So this week we're going to focus on gases and the behavior of gases. We'll go over a couple pretty simple things that you've already seen, and then we'll talk about what this means in terms of the individual gas laws that you need to know, and finally we'll finish up with some problems. So as you saw in the notes, gases are the phase of matter and the only phase of matter that doesn't have a shape and doesn't have a volume. We say they have indefinite shape and indefinite volume. The only thing that constrains the shape and volume of a gas is their container. Because gases take the shape of their container, we can do a lot of things to gas. We can squeeze them, we can expand them, we can release them, and over time, if they get into a bigger and bigger container, like when they fill a room, they'll get so diffuse they really won't be there anymore. Think of the smell of popcorn wafting across your house. We need a method to describe that behavior, and that method is called the kinetic molecular theory, or KMT. So the kinetic molecular theory was proposed in about 1860 by two scientists named Boltzmann and Maxwell. They're actually not working together, but they both come with this at the same time. And they make the same 5 assumptions about all gases. They are that individual gas particles are small. In other words, gases are mostly empty space. Gas particles are in constant random motion. Gas particles move in a straight line until they collide with something, and that's the only things it can collide with are other particles of the gas or the walls of the container it's in. So think about gas molecules bouncing off the inside of a balloon. No energy is lost when gas particles collide. In other words, collisions are elastic. And finally, the kinetic energy of a gas particle is determined by its mass and velocity. According to the equation, kinetic energy is 1/2 times mass times the square of the velocity. This means that the more massive the gas, the higher the energy it's going to have. So now that we know how gases behave, there were several other scientists who came up with what are known as the gas laws. And there are 4 gas laws you should know, and they are Boyle's law, Charles's law, Gay-Lussac's law, and the combined gas law. So one by one, they are as follows. Boyle's law says that the pressure of a gas and the volume of a gas vary inversely with each other. So as pressure goes up, volume goes down. And he has this equation that says if a gas is at one volume and one pressure, if you change the other one, it's going to equal the new volume times the new pressure. So we say it's P1V1 equals P2V2. Charles's law talks about the temperature and the volume of a gas and say they vary directly with each other. So as the temperature of a gas increases, so does the volume. It is written by the equation temperature over volume is equal to the new temperature over the new volume, or T1 over V1 equals T2 over V2. Then we have Gay-Lussac's law. I know it's spelled Gay-Lussac, but it's actually Gay-Lussac. And he talks about pressure and temperature. And he says as the temperature of a gas increases, so does the pressure. His equation is very similar. It is P1 over T1 equals P2 over T2. So pressure over temperature. If you change one, you can figure out the other. And finally, we can actually put all 3 of these together in what's known as a combined gas law. And this says that pressure and temperature and volume and temperature vary directly, like Charles and Gay-Lussac, and that pressure and volume vary inversely. So the way we write it is we actually write it as P1 V1 over T1 equals P2 V2 over T2. One of the unique things about being asked to solve problems involving the gas law has to do with temperature, though. When we solve problems with gases, the temperature is not in Celsius. So it's not in degrees Celsius. We'll put a line through it. Instead, you have to have the temperature in Kelvin. The Kelvin scale is based off this idea of absolute zero, where 0 degrees Kelvin is this point at which all matter stops moving because temperature is a measure of the motion of matter. The way we solve for Kelvin is very simple. Kelvin equals degrees Celsius plus 273.15. Sometimes it's abbreviated 273. but we add the 1.5 just for a little bit more accuracy. So it's really important to know that whenever you solve these problems, you have to convert the temperature back and forth from Kelvin all the time. And you'll see that when we go through these practice problems. So we have two practice problems here, and I'll go through them one at a time. The first one says a sample of neon gas at room temperature of 20 degrees C, there's a degree symbol there and on that one too, has a pressure of 108.3 kilopascals and a volume of 58.0 ml. So we have P1, we'll write them all out. We have P1 is 108.3 kPa. We have T1, it's 20 degrees C, and we have V1 is 58.0 ml. Then it says if the pressure is increased to 111.5 kPa, P2 is 111.5 kPa, while keeping it at room temperature, so T2 is still 20 degrees C. What is the new volume? So V2 is question mark, that's what we're trying to solve right here. The other thing you should notice is that because temperature 1 and temperature 2 are the same, we can actually ignore them in this problem and make this a very simple Boyle's Law problem, which says P1V1 equals P2V2. Solving, of course, for V2, this means it is P1V1 over P2, or 108.3 kPa times 58.0 milliliters, I didn't have room for that, divided by 111.5 kPa. When you solve this for 3 sig fig, you end up with an answer of, and I'll put this in red so you can see it, the answer is V2 is 56.3 milliliters. And that's really all there is to these problems. And we'll do the second one. Let me erase what I just did so you can actually read the problem. But this one says hydrogen gas inside a compressible chamber is held at a constant pressure of 0.976. That means P1 is going to equal P2, and we can just simply ignore it. So instead, let's focus on T and V. So we have, T1 is 12.4 degrees C, and V1, it tells us, is 17.3 liters. We then increase the temperature to 43.6 degrees C, and we don't know V2, that's what we're trying to solve. The question here, though, is we have to remember we have to convert these temperatures to Kelvin. So I'm going to add 273.15. That's going to make this 285.55. And I'm also going to change this one to 273.15, which makes it 316.75, and these are both in Kelvin. I can then go ahead and solve using Charles's law, T1 over V1 equals T2 over V2. I'm going to rearrange it by cross-multiplying and then figuring it out. So we have T1 V2 equals V1 T2. And then at the end of the day, V2 is equal to V1 T2 over T1. When I plug it all in, it's equal to 17.3 liters times 285.55 K over 316 point, whoop, I got these backwards. See, that's the tricky part of all this, is you got to make sure you put the right one for T2. So that's actually 316.75 K. See, I make mistakes too. And then this bottom one is going to be T1. So it's really important you write these out. That's why I write them out. 285.55. When I plug it into my calculator, I get a final answer of 19.2 liters. So increase the temperature by a little bit, and the volume goes up. So when you're doing these problems, you have to check yourself, and you have to make sure that the answer makes sense in terms of what kinetic molecular theory talks about. You also have to make sure you convert the temperature to Kelvin and that you're plugging these into the right place. So it's a little bit challenging. Finally, there's one more gas law we haven't talked about, and that's the ideal gas law. And basically what this says is how gases behave under ideal conditions. We can also put another factor in there, and that other factor is the mole. So for any gas, we have this equation that says the pressure times the volume of the gas is equal to the number of moles N times a constant R times the temperature in Kelvin. R is a constant, and you'll have to be given the value of R. They're in the notes section up ahead. R has a weird unit. It's usually liters of pressure. It's pressure times liters over moles times K. It helps everything cancel out. Temperature, of course, when we do this, has to be in Kelvin. And this N, as a reminder, this is moles. Obviously, P and V are pressure and volume. Ideal gas law problems are relatively easy as long as you use the correct R. Let's take a look at one really quickly. Here's one that says if I have 4 moles of a gas at a pressure of 5.6 atmospheres and a volume of 12 liters, what is the temperature? We simply use our equation PV equals nRT. In this case, we're trying to solve for T, so as we rewrite our equation, it's going to be T equals PV over nR. P is 5.6 atmospheres. V is 12 liters. It's really important when you solve these that the volume is actually in liters on this. N is 4 moles, and then R is a constant, and the constant is actually based entirely on what the unit for pressure is. So in this case, you can look it up in the notes, but because pressure is in atmospheres, the volume we're going to use for this is 0.0821 atmosphere liters per mole K. When I solve this all out, it's 5.6 times 12, which is equal to 67.2 atmosphere liters. That's a weird unit, but you'll see in a second. When I put that on the bottom, it's 4 times 0.0821, which is 0.3284. Moles is going to cancel, so it becomes atmosphere liters per K. When I solve that out, what's going to end up happening, see moles is going to cancel right there. The atmosphere liters are going to cancel. And when I solve it all out, I get T is equal, and this is where you have to be careful, 67.2 divided by 0.3284 gives me 204.63. We'll just round there. But that's in Kelvin. And we don't want it in Kelvin, so to convert to Celsius, we're going to we're going to subtract 273.15. When I do that, I get a temperature of negative 68.5. But then I need to check my problem, and if I check my problem, I have one sig fig here. So in all that, the answer is this gas is at a solid negative 70 degrees Celsius. Nice and chilly. So I went over a lot of this stuff very quickly today, and it goes into a lot more of excruciating detail. I'm not asking you a ton here, but this tends to be one of the more kind of robust units we do in the second semester of chemistry. I want to remind you that if you have questions on this stuff, we do have class Monday and Wednesday at 12:10. I'm also available to chat on Schoology anytime you want. Just send me an email and we can take care of it. But other than that, this will probably be the week where you have the most to do. It'll start to wind down a little bit. The next 2 weeks look really simple as the year gets on. I want to make it easier and easier on you. But this is probably the most robust week. It's the only week you have 3 things to do. So I wish you luck. I hope you guys are doing well. Take care of yourselves.